everyone. Okay, today we're going to go through Charles's Law. So Jacques Alexandre César Charles. Try to guess where he's from. So he's French. So his dates are 1746 to 1823. He's a French physicist. A lot of people, even though like it's a law that we take in a chemistry class, the sciences are all very much intertwined, and a lot of people who've won Nobel Prizes for chemistry are actually physicists or would consider themselves physicists. And actually some physicists have been a little angry that they won a Nobel Prize in chemistry because they're big snobs apparently. Now, so Jacques Charles, he researched hydrogen balloons. So this is hot air balloons. For whatever reason, during the early 1800s in France, there was a lot of hot air balloon research going on, and that interestingly led to a lot of the gas law discovery. All the sort of things we know about gases came from the fact that they were trying to figure out how to travel by the hot air balloons here. So he was actually one of the first people to ascend in a hot air balloon, and with the Roberts brothers. You can look that up if you're interested. Not much is known about him. He wasn't really a scientist, so he worked in finance first, and he came from a liberal, non-scientific education. So this gas law, all these gas properties, this all just came from him having a passion for hot air balloon travel. The law bears his name, but it was actually published by a scientist of Gay-Lussac, who we're going to learn about next lesson here. So Gay-Lussac actually first published it, but he was building on Charles's research, and so he just improved on his discovery. So just incidentally, this is all information. This is just background info. I don't expect you to memorize any of this stuff here. Now, so he did research with volume and temperature. So what he discovered was the fixed amount of a dry gas varies directly with the Kelvin temperature scale. Now, something varies directly, so we're going to have volume varies directly with temperature, and then we're going to have a little subscript K there, the K there representing the Kelvin temperature scale, and we'll talk more about that in a minute here. So because these vary directly, remember Boyle, which is P varies with 1 over V, those are indirect, so as pressure increased, volume decreased. So with volume and temperature, these are directly related, so we can say that as volume increases, temperature also increases. And we can think of, if you had, if we were in class, I would take a flask and I would put it on the hot plate and I would put a balloon over the top of the flask, and then we would watch as the temperature heated up, the gas inside the flask, that the balloon would inflate. So we would see that the gases were expanding. This makes sense also in terms of kinetic energy. If you think of a balloon, you've got your particles in here, right? Your gas particles. If you provide heat to that, I just basically want an excuse to use my stylus here, my pen. This is heat getting very, very hot. What's going to happen is that balloon is going to expand. It's going to get bigger and bigger because the particles now have more energy. They're going to be moving faster, moving farther apart. Okay, so that is how those two things relate to each other here. So the formula then, did I go red? The formula for Charles's law is going to be V1 over T1 equals V2 over T2. So you can memorize that. You're going to be using it a lot. That is the formula for Charles's law. So volume varies directly with temperature. Now, the Kelvin temperature scale, we have briefly touched on this because we talked about STP. And at STP, remember we said 0 degrees Celsius is equal to 273.15 Kelvin. So how we convert between these, So Kelvin is going to be equal to degrees Celsius plus 273.15. It's important to note that the unit for Kelvin is K. So there's no degree symbol. So you will never see this. That is wrong, okay? It is just K. There's no degree symbol. So let's work through an example here. Convert 32.1 degrees Celsius to Kelvin. So Kelvin is going to be equal to 32.1 plus 273.15, and that is going to be equal to, and we're going to get 305.25 Kelvin. Now, you do not worry about significant figures here. You just keep all of the digits here. Now, in terms of calculating your answer, like if it was a part of a bigger problem, you would look at the fact that this had 3 sig figs. But when you're doing your conversion, don't worry about significant figures. Now, the Kelvin temperature scale is derived from the concept of absolute zero. So absolute zero is the coldest possible temperature. And it kind of feels a little counterintuitive to me. Typically, it feels like you should just always be able to keep getting colder, right? But there is a zero. There's an absolute zero that you can't get any colder than. And that absolute zero is is equal to negative 273.15 Kelvin. So that is 0 Kelvin here. So the Kelvin temperature scale is based off of this concept. So 0 Kelvin is also equal to negative 273.15 degrees Celsius. Kinetic energy is equal to 0. So at this point, all molecular motion has stopped. So if nothing is moving, that means the energy due to motion, which is our kinetic energy, is also equal to 0. Now at this point, the volume of a gas would also be 0. So this is hypothetical, but because there is no molecular motion, everything would just shrink down, okay? So the hypothetical volume is also 0. Oh, here's a good joke. You heard about the guy who froze himself to absolute 0? He's okay now. Do you get it? Some of you don't get it, I know. Some of you will. He's okay. In other words, 0 Kelvin. Ha, ha, ha. I like this one. You may have seen this Chemistry Cat cartoon before and not known what it meant, but now you know. I'm sure you're very proud of yourself. Okay, so here's just a little example of showing the 3 different temperature scales that we're used to here. So let's go first, or these are all going to be 0 to 100. So 0 to 100, 0 to 100. So let's say the first one, this is degrees Fahrenheit, degrees Celsius, and Kelvin. So if we look at these different scales here, now, if you have degrees Fahrenheit, 0 degrees Fahrenheit, what would that feel like? Anyone know? Yeah, you're going to be cold. It's going to actually be fairly cold. You're going to feel cold. Now, what about 100 degrees Fahrenheit? Yeah, that's pretty hot, but people would experience that regularly. Places like Florida, down south in the States, you would fairly regularly get that hot. So cold, you're going to feel cold at 0, hot at 100. Now for degrees Celsius, how do you feel at 0 degrees? Yeah, it kind of depends, right? If we're in the fall, we're cold, but if it's in the spring, 0 degrees actually feels not too bad. So I'm going to say, yeah, we're going to feel coldish at 0 degrees. Now, how are you going to feel at 100 degrees Celsius? Yeah, you're going to be dead at 100 degrees Celsius, right? Because your water boils at 100 degrees Celsius. We've got water in our bodies. You're not going to be living then. What about 0 Kelvin? That's absolute 0. Are you going to be alive? No, you're going to be dead. What about 100 Kelvin? You are also going to be dead. So that's just a quick little analogy in terms of getting you used to the differences in the 3 different scales. So they are quite different, which is why Charles' law here only works for this one, because these scales are not the same. All right, I'm going to go back to green. We must convert all temperatures to Kelvin in order to use Charles's law. So you got to get used to working in between the different units and converting between the units. Now we've got a formula, which is Kelvin equals degrees Celsius plus 273.15. So if we're solving for degrees Celsius is going to be equal to the Kelvin minus 273.15. So that's going to be 183.5 subtract 273.15 is going to be equal to 183.5 subtract 273.15. So you are going to be equal to negative 89.65, and the unit there, degrees Celsius. Now the other way, convert 27.24 degrees Celsius to Kelvin. So Kelvin, again, degrees Celsius plus 273.15 is going to be equal to then 27.24 plus 273.15 is 27.24 plus 273.15. So my windows are open and you may be hearing my children yelling right now. I'm not sure what the speaker will pick up here. 300.39 Kelvin. Okay, so you have to get used to doing those conversions, which should come pretty quick to you. Okay, we're going to do an example now of using the actual law, Charles's law. Again, I would recommend writing a variable list down the side. So V1, T1, V2, T2. Okay, so if the temperature of 6 liters of gas, so right away we've got 6 liters of gas at 25 degrees Celsius is increased to 227 degrees Celsius, determine the volume at the new temperature. So question mark there. Okay, so we're going to just write our equation, or actually we're going to do our conversions for Kelvin first. So you're basically just going to take the degrees Celsius and you're just going to add 273.15. So I'm going to go ahead and do that. So this one is going to be 298.15 and 227 plus 273. Oops, hold on. This one's going to be 500.15. Good, so now I've got those converted into Kelvin, so now I can solve. So V1 over T1 equals V2 over T2. Now I'm going to solve for V2. So if I rearrange these formulas, I've got a little trick here, which some people, my chemistry teacher in high school taught it to me, and I've used it ever since. It works really well. If you have a situation like this, sometimes people get confused with the algebra. So an easy way to rearrange it is you circle what you're looking for, and then if you just draw a diagonal line, everything on that diagonal line goes to the bottom. So T1 is going to go to the bottom. Left over is our V1 and T2. Those are going to go to the top. So now I can just sub in my values here. So it's going to be 6 multiplied by 500.15 divided by 298.15. Sorry, I ran out of space. It's going to be equal to, so 6 times 500.15 divided by 298.15. And I get an answer of 10.06. But I'm going to check my sig figs here. Yeah, if I look here, I have to look at those 3 pieces of information, and those are 3 sig figs only. So 10.1. And my unit is going to be liters. Okay, so that's going to be the answer there. 10.1 liters. Now, okay, I'm going to give you the assignment, but before I do that, let's just practice rearranging here. So V1 over T1 equals V2 over T2. let's say that I asked you to solve for T1. It's a bit of a pain algebraically. You have to do, multiple steps of algebra to solve for T1 to get that in the right spot. So if you use the trick that I showed you, just circle what you're looking for, draw a diagonal. So now T1, everything on that line goes to the bottom. Everything else stays on top. This honestly will help you. Please take the time to learn this right now. And as the formulas get more complex, this little trick comes in really handy. So yeah, just rewatch that part if that's confusing for you, or send me a message and I can go over it with you. So exercise 5 in the booklet is assigned. It's really, you're given 3 variables, asked to find the 4th, so it shouldn't be that difficult for you. Take a look at it and then message me if you have any questions. Okay, thanks a lot, guys.